modified Euler's method. Okay. So in the modified Euler's method, right? So what we are going to do is, so earlier in case of Euler's method, suppose if this is the curve, then actually this is one point x naught, and here this is x naught plus h. This value is y naught and this value is y1. Now we wanted to calculate the value of y1 with the help of Euler's method. So Euler's method, for solving the differential equation of the form dy by dx is equal to f of x comma y. Now this is nothing but the slope for us. So this is the slope for the curve at that particular location, which essentially the tangent curve. If you draw a tangent here, so this is the tangent slope, this is the dy by dx at x naught comma y naught. So this is the tangent slope there. Now here, if you want to find out this value, we have approximated this as the value rather than the ideal value of y1 here, because this is with the help of numerical methods we can approximately calculate it. We cannot calculate the 100% accurate value. So there actually, if you want to put it here, so this is the value which we are going to calculate it, and then that value you can calculate from this triangle of, this is theta, then tan theta is the slope. So this is the tan theta value, and then tan theta is nothing but opposite side by adjacent side. So this one, ideally this should be the actual, but this is the approximated value of the y. So approximated value of y is nothing but y1, and then this difference is y1 minus y naught, y1 minus y naught divided by this difference is h. So h, this value is equal to dy by dx at x naught comma y naught. So this is the slope at that location, and then y1 minus y naught, this is equal to h times of dy by dx at x naught comma y naught, and then y1 you can calculate as y naught plus h into dy by dx at x naught comma y naught. So this way actually you will be approximating this value as the y value, and then from there actually you will further calculate if at all you want the next value as x naught plus 2h. Got it? Yeah. So any questions on this Euler's method? Any questions? Okay. So now come to the Euler's modified method. So modified Euler's method, what we are going to do is, here actually we tried approximating y1 as the new value there, but rather than that, if you try to predict this value more closer to this one, then actually that will be the actual value we can think of. Now for that, the procedure what we are going to follow is, here when we calculate the y1 value, we have calculated the slope at this point, and then we have used that slope as the dy by dx at that location, and then multiplied with h and then added to this one. Rather than that, this value, if I make an average of this slope from here to here with the new calculated value of y1, then I am going to get a better approximation, because here actually the slope value based on this curve, if you calculate it, this is how is going to be the tangent that you can draw, which is parallel to this curve but located at this location. So that is a new slope, and if you take the average of this slope between this slope and this slope, then actually you are going to get a better value of this slope, and then based on that better value of this slope, if you are able to calculate the y value, you can further approximate to this location, which is a next approximated location for the same y1 there. So for that, this y1, so y1 actually I call this as y1 dash, and this value is y naught plus, now the average of the slope, so h, and then dy by dx at x naught y naught and dy by dx at x1 y1. So you have to take the average of this, that is dy by dx at x naught comma y naught plus dy by dx at x naught plus h comma y1. So this y1 actually which we have just calculated here. So this value is getting used here, and then x naught plus h, and if you take the average of these two, you are going to get a better approximation there. So this value, if I replace in terms of f, then y naught plus h by 2 times of f of x naught comma y naught plus f of x naught plus h comma y1. So this value is the better approximated value than the previous y we have calculated, and this is y1 dash. Now you can make use of this better approximated value for the second calculation of the slope, and again take the average of these two. You still get a better approximation which is far closer than this. So that is, if you want to calculate y1 double dash, then this you can calculate as y naught plus h by 2 times of f of x naught comma y naught plus f of x naught plus h comma y1 dash. So y1 dash will make a better approximation for y1 double dash. Similarly, y1 triple dash you can calculate as y naught plus h by 2 times of f of x naught comma y naught plus f of x naught plus h comma y1 double dash. It will give a still better approximation. And then this y1 dash, as long as actually these two values are very, very closer to each other, then you can stop calculating from there, and then you can shift to the next value of y2, so which is y1 plus, and whatever the y1 we have calculated here, this we treat as a new y1 for us, which is the actual value of y1, which is very, very close to this location, or actually almost 100% close to that location. From there, you can try to calculate the next approximated value for the y2. So that is y1 plus h times of, in the first case actually you calculate straight away y2, that is h times of f of x naught plus h comma y1. So this is y1 and h times of f of x naught plus h comma y1, and this value will give y2, and then this you can make use to calculate y2 dash. This is equal to y1 plus h by 2 times of f of x naught plus h comma y1 plus f of x naught plus 2h comma y1 dash, sorry, y2. So this value you can make use to calculate the next value. Similarly, the same procedure continues till you get a better value for y2. This better you can decide based on the consecutive iterations. If you are getting more or less the same value, then you can conclude that you cannot improve further to that number. So usually it will be 2 to 3 steps it will take for a better calculation of the same value in the iteration process. Got it? Any questions on this Euler's modified method? Any questions? So if there are no questions, just you can note down this. We are going to solve a problem on this. So note down this problem. Using modified Euler's method, find an approximate value of y when x equal to 0.3. Find an approximate value of y when x equal to 0.3. Given that dy by dx equal to x plus y, given that dy by dx equal to x plus y and y is equal to 1 when x equal to 0. So this is the information it was provided. Here, if you want to use the Euler's modified method for calculation of y1 itself, actually we take more number of steps. And similarly, to calculate y2, you will take more number of steps. So based on that understanding, you try to solve on your own first. I will give you 2 minutes time. Afterwards, if you need, I can solve it. So for simplicity purpose, consider h is equal to 0.1. That means you have divided the entire curve into 3 different equal intervals. So this is 0, and this is 0.1, this is 0.2, and this is 0.3. So here actually we need to be finding the value. For the curve, dy by dx equal to x plus y. Right? In the modified Euler's method, so what you can do is, you can prepare a table x, y, dy by dx. Then once you calculate dy by dx, which is equal to x plus y, and then here you can calculate the approximated value of y. So y1 or y new is equal to y old plus h times of f of x old comma y old. So in case of modified Euler's method, so this is going to be h by 2 times of this one plus f of x new plus y new. So this is the equation which you can make use to calculate the value of y. Now here, if you take the first iteration, let us say 0.1. So first is actually 0. At 0, the value of the function is 1. And then dy by dx value is x plus y. So this x plus y, you can add these two. So this is 1. And then y1, you can calculate as, so being this is the first iteration, what you can do is, this is y naught plus h times of f of x naught y naught. So this value is going to be y naught is 1 plus h is 0.1 multiplied by f of x naught y naught. This is again 1 here. So this is going to be 1.1. So this is actually same value when we have calculated with the help of Euler's method or even with the modified Euler's method. The first line is going to be same, but the second line is going to be changed. Here x is, so again this is going to be, so this one for the 0.1, so this is going to be y1 value, what we have calculated here, it is 1.1. Then the sum of these two is 1.2, and then here when you are trying to calculate this y1 value, you can calculate with this particular formula. Got it? Yeah. So this way you proceed further and then actually try to calculate it. See this, for the second one actually you have to use this formula, not this one. This is only for the first iteration. So for rest of the iteration you can use only this formula. What we are trying to do here, it is, you have drawn a tangent here and this tangent will cut here. Now here actually in the second step what we are trying to do is, you take the slope from here and slope from here and take the average of that two, and then actually you can make use that value of the average slope to calculate the better value of y here itself. So here itself we are taking 3 iterations. So here actually, so this is 1.2, and this one, if you want to use this one, then so this is y1 dash is going to be y old is 1 plus, sorry, y old is 1.1 plus, and then the average of this slope, this is 0.1 by 2 times of the average of the slopes is here the slope is 1 and here the slope is 1.2. So this is 1 plus 1.2. Yeah, so 1 plus 1.2. So this value you can calculate. So this is 2.2. 2.2 by 2 is 1.1. 1.1 is 0.11. 0.11 plus 1.1. This is 1.21. So this is a new value of y1. Now again, if you want to calculate y1 double dash, here what we can do is x is again 0.1 and y1 value actually we have calculated as 1.21, and then the sum of these two is 0.1 plus this is 1.31. So 1.31 is the new slope here. Now here the previous value, here it is 1.21 plus 0.1 by 2 times of. So here actually you are again considering the slope at this location and here new calculated slope. This location slope again is the initial slope, that is 1, plus the new value of this slope is 1.31. And then you can take the average of these two and then calculate it. Got it? Oh, sorry, I think so there is a mistake here. So rather than this, right, so we will calculate the average slope here itself so that our formula will be better. The average slope you can consider here, and then here actually you can calculate y new. So this is y volt plus h into average slope. So this way table will be better. So this is, first one is 0 and then the y value is 1 and the average slope actually initially there is nothing like average slope. There are actually, this is the only slope we can think of. So hence here y1 you can calculate as y volt plus h is 0.1 times this value. So the slope value is 0 plus 1. So this is 1. So this is going to be 1.1. And then you can use this value now. So to calculate the average slope. And then initial slope here actually, so initial slope is the sum of these two is 1. Now here when you are considering the average slope, 1 by 2 times of this slope plus the new slope, what we can calculate as sum of these two. This is 1.2. So this is the average. So the sum of these two is the slope. So this is x plus y. 0.1 plus 1.1 is 1.2 and the previous slope is 1. So the average of this is 2.2 divided by 2. This is 1.1 again. So y1 dash is equal to initial value of y is y1 plus 0.1 times of, again this is 1.1. So this is 0.11. So 0.11 plus 1. 1.11. Now you can calculate the next iteration, 0.1 and 1.21. The sum of these two will be the slope. So 0.1 plus 1.2, 1.11. So 0.1 plus 1.11. So this is 1.21. So 1.21 plus the initial slope is again 1 and this value is 1 by 2. So don't consider this slope. So this is always there. If you notice, this one comes in every iteration, in the next one also. So this one is the initial slope, that is the slope at this location, and here actually the slope keeps on changes when we are calculating the average. So this is the only slope that is going to change. This won't change. So this value is anyway 1. So here the average of this is 1 plus 1.21. So this is 2.21. So by 2. So 2.21 by 2 is 1.105. So y1 double dash equal to 1 plus 0.1 times of 1.105. So this value you have to calculate it, and then here 1.1105. Now if you take the next iteration 1.1105, and then this is again 0.1, and half of this 1 plus, so 1.2105, and then y1 triple dash equal to 1 plus 0.1 times of, so this is 2.2105 by 2, 1.1025. Yeah, I think you can stop there. So this is 1.110. I think so. You calculate this value. I think so. This is more or less 5 only. Yeah. Yeah, 1.105. So this way you can calculate the value of y1. So once you arrive at this value, if you notice here actually this is repeated. Once you get a repetition, then you can think of the next iteration. Akhil, what is your question? Do you have any question? So this is always y naught. So here actually this is always y naught. Maybe in the previous iteration I think you asked. Yeah. Yeah. Okay. Fine. So this one actually we have calculated y1. So once we calculate y1, then actually you can calculate y2. That is 0.2. So when we calculate 0.2, then here actually whatever the slope you finalize, that slope is this one. So you have calculated y1 triple dash as the y1 value. So this value is 1.105. Then you can calculate this value as, here the value is at 0.2. So whatever you have calculated there, so 0.2, and the value of the y is going to be, you can consider as 1.1105 as the value, and then in the so you can calculate the sum of these two. This is 1.2105. So this is the slope there. Now this slope you can make use in the first iteration, and then you can calculate. So there is no average you can think of, because actually you have considered only one slope in the first iteration. So 1.2105 is the slope, and then you can calculate y2 is equal to y1 plus h times of f of x naught plus h comma y1. So this y1 is this value. Got it? So here y1 is 1.1105 plus h is 0.1, and then f of x naught plus h comma y1. So this value is going to be, you can calculate this as 1.2105. 1.2105. So this value is y2 for us. Now in the next iteration, we calculate y2 dash. Exactly in the similar procedure. When we are considering that, you take the average of the slope. So let us say this is y0, this is y1, and this is y2. So when we calculate y2, so here actually you have to consider this slope, and then you have to consider the slope at this location, assuming this curve. So this is the new slope. The average of these two you need to consider for a better approximation closer to y2. Similarly for y3. Got it? Understood? So the answer is 1.4004. Y at 0.3 is 1.4004. 4004. So this is the answer. Got it? So this way, like actually, you can make use of Euler's method and Euler's modified method. See this exact for point 1 and point 2, it won't make any difference. Here actually, in the first case actually, you have calculated as the one slope, right? So initially when we calculated, we have not taken any average slope here because actually we have only one. This one actually straight away you have considered the slope here. But here when we consider here 1.1 is coming from the average of these two slopes. So here you have calculated the previous slope and then actually you have make use of that value in the calculation of the next one for taking the average there. First, okay, let me solve for point 2 also. This is x and this is y. This is the average slope. This is y nu is equal to y volt plus h times of average slope. So this is the equation what we can think of. So in the previous iteration, we have got for point 1 as 1.2105. Then the corresponding slope, so this is not an average slope. So here the slope for this first iteration is going to be the sum of these two. So you are not considering the average slope here in the first iteration. So this is 1.3105, 1.3105, not average. So this is the value of the slope at this location for point 1. Now here y nu is y2. You can calculate as, so y volt is 1.2105 plus h is 0.1 times this slope 1.3105. Now this way actually you have calculated y2. So this value is coming out to be 1.2316. So this value is 1.2316. Now in the calculation of the next one, what you will do is, this is 0.2 and then this value is 1.2316 and then here actually the previous slope is 1.2105 plus 1.2316. Sorry, the sum of these two 1.3105 plus the sum of these two is 1.4316 and then take the average of these two. So this average value you have to consider. Now when we calculate y2 here, this value is y volt is whatever we have calculated is 1.2316 plus 1.2105 plus h is 0.1 times this average slope. So this value is 1.3105 plus 1.4316 by 2. This value you have to calculate it. So this value is coming out to be 1.2426. So this is how you can calculate. And in the next iteration again, you take this value here and then this is 0.2 and 1.2426 and then sum of these two will be the slope and take the average of 1.3105 and this value. Got it? this value is here 1.2105 here, and the y value I have made mistake. So y value is not that one, 1.1105. Yeah. So here the same value whatever is here it comes 2105. Yeah. Got it? So you are considering the previous y value, that's all. Yeah. So any questions on this Euler's modified method? So in this, right, so the method whatever we have discussed, right, so there is something called a series of methods or the order of the methods for finding out these ordinary differential equations. So in the ordinary differential equations order, so there is a first order, second order, third order and fourth order. So these are called first order. Method to find the solutions of ODE. So this first order, so in general it is called as Runge-Kutta. Runge-Kutta first order. And this is what is Euler's. So this is the Euler's method. And then Runge-Kutta second order method is called as modified Euler. And the next one is Runge-Kutta third order, and this method is Runge's method. And the next one is Runge-Kutta fourth order method. So this is in general called as Runge-Kutta's method. Got it? So these are the four different types actually what we can make use to calculate the solutions of the ordinary differential equations. Now the first one anyway we got to know, that is Euler's method, and the second one also we got to know, and then here actually there were improvements in taking care of or the finding the solutions in this order. So this is first order, second order, third order and fourth order. So this is most popularly used for all the calculation purpose. So these two methods actually followed one principle, but in the next one actually it follows Simpson's one-third rule. So these two actually follow Simpson's one-third rule. To find the solution. Got it? So in the Simpson's one-third rule actually how it is getting used is, so first you note down this, I am going to draw a diagram and explain. Then okay. So how we are using this Simpson's one-third rule in finding out the solutions is, so in the ordinary differential equation the way we solve is we make use of the integration so that actually you can find the solution between the x and y. So here exactly in the similar manner, let us say this is the curve which we wanted to trace, and this is x-axis and this is y-axis. Now finding the solution meaning, so this is x naught and this is, let us say, x naught plus h. So this is the next one and we wanted to trace this value of y. So this is going to be y naught. Now the differential equation is, let us say, dy by dx is equal to f of x comma y. So this value actually which we wanted to find out the relation between these two. So as we go in the normal integration method, dy can be given as f of x comma y into dx. Now if you integrate on either sides, this integral value can be written as integral y naught to y naught plus k dy is equal to integral x naught to x naught plus h and f of x comma y dx. So this is how actually you can write the integral value. So y becoming y naught to y naught plus k. This k is the new value of y for us, which will give this value. So this is as if like y1 is equal to k for us. Now this k value which we wanted to find out. For that, what we are doing here it is, this is just a curve. And this curve actually dx getting multiplied and tried integrating from x naught to x naught plus h, which essentially whatever the curve we are talking about, for that curve, this is the area under the curve with respect to the x-axis. That means this is the area. So this area is the value of the integration for us. Now this area we can find out with the help of Simpson's one-third rule. By dividing this x naught and x naught plus h as two different intervals, by taking the midpoint here which is at x naught plus h by 2. So this is the midpoint. Now we calculate this area with the help of Simpson's one-third rule by considering two different parts. So this is one part and this is another part. So for that actually what we have known is, so first actually you draw a tangent here. So this is the tangent here. Now here actually this line is cut at this location and last line it cuts at this location. Now the slope at this particular point for this particular curve you can draw at this location like this. So this is the slope which is a tangent to this curve. So this is the tangent and here the slope may be different and this is actually a tangent at this location. Now we calculate the slope at this location and this location for the same curve at different intervals, and then you can take the weighted average of that, which will be the Simpson's rule again. So now actually let us see how it is going to be. Here actually the function value is x naught comma y naught is the function value here, and here actually the function value is going to be f of x naught plus h by 2 comma so y1. So I call this as k by 2. Yeah. And then here actually the last one is f of x naught plus h comma k. So this value actually, the slopes actually what we can calculate with the help of this functional value. Now here when we wanted to find out this integral value, here this integral is integral dy is y, and then upper limit is y naught plus k and the lower limit is y naught equal to integral x naught to x naught plus h f of x comma y dx. Now this value is y naught plus k minus y naught. So this you can treat as k, because these two will cancel out, and this k value is nothing but x naught to x naught plus h into f of x comma y dx. So this k value actually which we are finding out now. Got it? Yeah. So any questions till this point? So this k value actually we are finding it now. So this k value when we wanted to find out, here actually this value is x naught plus h by 2. So this is the function value at this location, and here actually x naught plus h, and this is the function value at this location. Now if you want to find out the height increment, so this is the horizontal line, this is the horizontal line, or actually let me draw the diagram again. Now here, this is a tangent. This tangent, if you draw a horizontal line here, and this is at y0, this is also at y0. Now here, this height, if you are able to find out, you will get to know this particular value of the y at this location by taking this as the theta, and the slope at this location is dy by dx at x0 comma y0. This value is f of x0 comma y0. So this is the slope. Now here, if you want to find out this height, so I call this as a, b, c, d, and this location as e. Now BE is nothing but this slope into this length into tan theta. So that is BU is equal to h by 2 times of tan theta naught. So tan theta naught is nothing but this value, and this value is h by 2 times of, so f of x naught comma y naught. So this value is this height. Now this height actually y1. So I call this as, so this is y1, but here actually we can put a different name. So f, g and h. So GB is equal to y naught plus h by 2 times of f of x naught comma y naught. And then here CD you can calculate as y naught plus h is this length, entire length, h times of f of x naught comma y naught. Now you have calculated the height, this value and this value, which are the better approximated values. So here actually x naught, y naught, and here it's not x naught plus h by 2 and y1. So here actually it's not y1, rather than y1 actually we have calculated a value which is closer to y1, and even here also we have calculated value which is closer to this value, but it's not y1 here. Got it? So here actually we tried calculating here. So once you calculate this value based on the new calculated values of y, so this is CD is new y at this location and GB is new y at this location. So use these two values to find out the slope at this location and to find out the slope at this location. So these two slopes actually you can take a weighted average the way we have done in the Euler's modified method, which will give the solution for this Simpson's rule. So this actually you can divide into 3 different intervals. So 2 different intervals with 3 different points here. Now for that actually if you want to apply the Simpson's 1/3 rule, so here actually you need to consider the slope, and here you need to consider the slope, and here you need to consider the slope. Slope essential means for us is the functional value at that location. Got it? Yeah. First you note down this. I'm going to erase it and then I will try to use the Simpson's rule from this particular principle. So this diagram. So okay. So it was noted down. So what we are trying to calculate here, it is k is equal to integral x naught to x naught plus h and f of x comma y dx. So this value actually we wanted to calculate. This is actually as if like finding out the area under the curve. And for finding out the area under the curve, actually we have divided into 3 different parts, 3 different points and 2 different parts. Now, so if Simpson's rule is used for calculating the area of any random curve, this is x0 and this is x1 and this is x2. So for this actually the Simpson's rule, if you want to calculate it, let us say this is the function f of x0 comma, sorry, f of x comma y is the function represented by this, or actually f of xy equal to 0, or this is the function which represents this particular curve. Now for that what we have done, so the area under the curve is h by 3, where h is this length. So this is the h value, and h by 3 times of, so the first value and the last value, that is y0 plus y2. So this is y0 and this is y1 and this is y2. So first value and the last value plus 4 times of odd. 4 times of odds are y1 plus 2 times of even. So no more even, hence actually it is going to be 0. Now here h by 3 times of y0 plus 4y1 plus y2. So this is the Simpson's rule which you can make use to calculate the area under this particular curve. Now exactly the same thing what we are trying to do it here. Now here if you want to if you know the value of y1, then actually you can make use of this Simpson's rule. But here the complexity is the y value is not known, but we are trying to calculate a approximated value of y there. How we are calculating here it is, what we are doing is, you know the slope of this particular function here, because actually x0 y0 value we know already. If you know the x0 and y0 value, you will be able to calculate the slope of the tangent here, because the given differential equation is dy by dx is equal to f of x comma y. Dy by dx is nothing but the slope of the equation, and then slope value is expressed in terms of f of x comma y. So that slope actually you have drawn like this. So this is the tangent now. So this tangent actually you can make use of the tangent as to find out this height and this height which you can fit for this y1 and y2 rather than the ideal values which are located at these locations. Got it? Because we are trying to calculate an approximate value which we cannot calculate with the help of this method, the 100% accurate value. So you can calculate this value and this value by taking a tangent like this and then try to calculate the value here with the help of this GB equal to. So what we are doing is y0 plus this length whatever is there, this is actually h by 2, because x0 to x0 plus h is the h distance. So half of this is h by 2. H by 2 times of tan theta will be the length from B to E. So BE. So this is y0 plus h by 2 times of f of x0 comma y0. So this is GB value which you can make use in place of y1 here. So ideally actually this is not y1, rather actually you can call this as y1 by 2, because this is at half of this. So that's why y1 by 2 and this is y1 here. So similarly you can calculate this HD value. So this we can call as y1 and this value is going to be y0 plus h times of f of x0 comma y0 value. Got it? Understood? Where is E? So E is this location. So this location is E. So this is B. Got it? So in place of actually y1 and y2 actually you are calculating with this particular slope. But actually for a better approximation of the slopes at these locations actually you can make use of the next approximated values are nothing but the next slopes, because actually you have calculated the new value here itself. So here y0 is there, in the next one when you want to calculate it, so y1 is treated as y0 plus h by 2 times of f of x0 plus h by 2 y1 here, y1 by 2. And similarly y1 you can calculate as y0 plus h times of f of x0 plus h comma y1. So this value actually you can calculate it. See here actually in the first iteration actually what we are trying to do is you are taking f of x0 comma y0 as the initial slope. Once you get the values of y1 and y2, so this y and this y value, once you get it, what you are trying to do is you are using those calculated values to get a better approximated value by considering the slope at this location with the help of this formula. See this. So h by 2 times of f of x0 plus h by 2 comma y1 by 2. So this is actually rather than that. So this you can call as y0 plus k by 2. And then here actually x0 plus h and y0 plus k. So this is how actually you can write it. So there are two steps that are involved. In the first step, take the slope and calculate this value. and calculate this value. And then in the next step, when you are using that value for the Simpson's one-third rule, you will take the slope at this location and you will take the slope at this location for getting a better value of y at this location and for a better value at y at this location. So that is, so y at the middle point, y1 by 2, y naught plus h by 2 times of f of x naught plus h by 2 comma y naught plus k. But initially actually we have calculated the k value. And then in the next one, y1 is equal to y naught plus h times of f of x naught plus h comma y naught plus k. So these values actually which you can make use in the substitution of this Simpson's one-third rule. So once you calculate these values, I call this as k1 and I call this as k2, and then initial value is k. Is that the convention? Let me check it. k1, k2, k3. So is this noted down? So in general, for the application of this Ranges method, what we are using is, there are different constants that we are using. One is k1 is h into f of x naught comma y naught. Then k2 is h into f of x naught plus h by 2 comma y naught plus k by 2, k1 by 2, and then k2 dash, k dash, h times of f of x naught plus h comma y naught plus k. This is k value. K3 is so here actual k1, yeah. K3 is h times of f of x naught plus h comma y naught plus k dash by k dash here. Then when we are finding out the value of the integration, that is k is equal to 1 by 6 times of k1 plus four times of k2 plus k3. So this is actually the Simpson's one-third rule to calculate the increment value of k. Here actually, ideally we should be getting 1 by 3, but actually why we are getting 1 by 6 is this length is h by 2. So being this is h by 2 in the interval, so ideally this has to be h by 2 times of 3. So this was the h for us. So k is equal to finally h by 6 times of k1 plus 4k2 plus k3. So this is the rule. Got it? Understood? See this, here actually k1 value. So whatever the k1 value we have calculated here, that you are using here, k1 by 2. And then you are getting k2 value. And k dash is x naught plus h and y naught plus k1 again. And then you get k dash. And then k3 value is h times of f of x naught h comma y naught plus k dash. So this value you are using here, and then this value you are using here, and the same value you are using even here as well. Got it? Okay. So apply Ranges method. So these formulas you have to remember actually. Apply Ranges method. to calculate an approximate value of y when x equal to 0.2. When x equal to 0.2, given that dy by dx is equal to x plus y, given that dy by dx is equal to x plus y, y equal to 1 and when x equal to 0, and y equal to 1 when x equal to 0. So we need to remember the formula. This is k1 is equal to h into f of x naught comma y naught, then k2 equal to h into f of x naught plus h by 2 comma y naught plus k1 by 2, and then k dash is equal to h times of f of x naught plus h comma y naught plus k1, and then k3 equal to h into f of x naught plus h comma y naught plus k dash, and then k equal to 1 by 6 times of k1 plus 4 times of k2 plus k3. So these are the rules. So here if you notice, in the denominator it is 6 and the sum of the coefficients is again 6. So essentially this is actually the weighted average of the case. And if you notice the weighted average, right? So K3 is given 1 and K1 is given 1, but K2 is given 4 times. Now K2 value is actually in between the middle point. So that is actually the central value. So central value has got the higher value, and the last one is given the less weightage, and the first value also is given the less weightage, so that you can consider as the average value, so which is the Simpson's 1/3 rule. Now you can calculate these values. So x naught, y naught actually 0 and 1, and then the function value is x comma y. So f of x comma y is equal to x plus y, and it implies f of 0 comma 1 is going to be given as 0 plus 1 is equal to 1, and then h is you can consider. So maybe actually you can go in 2 different steps. I think in the textbook it was directly taken as 0.2. So h is equal to 0.2 if you take it, and then this value 0.2 times of k1 equal to 0.2 times of 1. So this is 0.2, and then k2, this is 0.2 times of f of x naught plus h by 2. So x naught value is 0 and h by 2 is 0.1, and then y naught plus k1 by 2. So y naught is 1 and k1 by 2 is 0.1. So this is 1.1. Then the sum of these two, this is 1.2. So 1.2 into 0.2. So 2.4 into 0.24. Then k dash is equal to 0.2 times of x naught plus h. So this is f of 0.2 comma y naught plus k1. So y naught is 1 and k1 value we have calculated as 0.24. So 1.24. So sum of these two is 1.44. Similarly, k3 equal to h times of f of x naught plus h is f of 0.2 comma y naught plus k dash. So y naught is 1 plus k dash is 2.44. So the sum of these two is So 1.44 multiplied by 0.2. So that is 2.88 and 0.288. And this one 0.2 times of 0.2 plus 1.288. 1.288 is 1.488. 1.488 multiplied by 0.2. 1.488 multiplied by 0.2. So this is 0.296. .296, and then the weighted average of this is 0.2426. 0.24 plus 4 times of 0.28 plus 0.296. So the answer is 0.2426. So 0.2426 is the k value. But when we wanted to state the value of the function at x is equal to 1.2, so f of at x equal to 0.2, the y value is going to be given as the initial value 1 plus the final calculated value as 0.2426. So y is equal to 1.2426. So this is the y value. Got it? Yeah. Any questions on this? So only thing is you need to remember this formula. That is very important. So in the Runge-Kuttas method, right, what we are going to do here it is, so we will be recalculating the values at the midpoint at h by 2, and then rather than giving per k2 4 units, we will divide two different parts, and then 2k2 and 2k2 dash, like that actually we will get it. That is the only difference. So there actually in Runge-Kuttas method, so this value is getting divided into two different parts again. So this 4k will be written as 2k plus 2k, like that. So that is that we are going to discuss is tomorrow. If you have any questions on this, you can let me know now. Any questions? So that's all for today. Thank you. Yeah, good night.